In this video, we will learn how to find out the utility maximizing bundle for a consumer which faces a specific utility function. The question is, a consumer faces a utility function that is utility is a function of two goods x and y, which is equal to under root x times y, where x and y are the two goods. If price of good x and y are $5 and $3 respectively, and has an income of $10, find utility maximizing bundle. Options are being given. We need to find out the correct option. Okay, so what we are being given? We are being given the utility function, that is utility is a function of two goods x and y that the consumer faces, which is equal to under root x times y. This is being given. Okay, price of good x is being given as is, we are being told the price of good x is $5, so it is 5. Price of good y is $3. Income of the consumer is being given as is $10. We need to find out the utility maximizing, that is, we are supposed to find out the utility maximizing bundle that this consumer will choose. Okay, since the question is related to the maximizing choice, that means our endeavor will be to maximize the utility of the consumer, which is being given us is under root x times y, subject to the budget constraint that he faces, that is price of x times units of x plus price of y times units of good y should be equal to the income. Okay, specifically here we are being told the price of x is 5, so we can write 5 times x plus price of good y is 3 times y should be equal to, and income is 10. So with the given utility function, rather with the given budget constraint, consumer wants to achieve highest satisfaction. Graphically, what exactly is meant by this? If I draw a simple graph here, we have good x on the horizontal axis, y on the vertical axis. With the given budget line, let us say this is our budget line, consumer's endeavor is to reach to the highest possible indifference curve, and optimality or maximization occurs where the indifference curve and the budget line are tangent to each other. That is the first order condition for maximum. Okay, so for optimization, for optimality, what is the condition? The condition is the marginal rate of substitution between good x and y should be equal to the ratio of the prices, that is price of x upon price of y. Now MRS, we know it is simply the ratio of the marginal utility of good x and marginal utility of good y should be equal to the ratio of the prices. MUX is simply the change in the utility due to the change in the consumption of good x, and MUY means the change in the total utility due to the change in the consumption of good y should be equal to the price of x upon price of good y. Given this utility function, can I write it like this? X raised power 1 upon 2 times y raised power 1 upon 2. Okay, so du upon dx means the partial derivative of this function with respect to x. So exponent of x becomes coefficient, so we have 1 upon 2. X raised power, exponent of x gets subtracted by 1, so we get minus 1 upon 2. Y raised power 1 upon 2 will remain same because we are taking partials with respect to x. Symmetrically, likewise, here we will get exponent becomes coefficient of y, so we have 1 upon 2. X raised power 1 upon 2 will remain same, but the exponent of y will be subtracted by 1, so we will get minus 1 upon 2 should be equal to ratio of the prices. Prices are, here it is 2x, rather price of x is 5 and price of good y is 2. Okay, 1 upon 2 gets cancelled here. Okay, now what will we do here? We do here basic calculation, that is we transpose this y to numerator and this x to numerator. So we will get, so we have y raised power 1 upon 2. If I transpose this, it gets multiplied, but its exponential sign changes. It is minus upon 2, it becomes plus 1 upon 2. Similarly, here we have x raised power 1 upon 2. If I transpose this, it gets multiplied, but exponent sign changes to from negative to positive. Okay, basic algebra should be equal to 5 upon 2. Here bases are same, we can add the exponents, which means we get here y raised power 1 upon 2 plus 1 upon 2. In the denominator we get x raised power 1 upon 2 plus 1 upon 2 should be equal to 5 upon 2. So 1 upon 2 is 1, which implies y upon x is equal to 5 upon 2. Okay, let us solve for y. Y will be equal to 5 upon 2, transpose, it gets multiplied, so we get x here. Now what will we do? We plug y is equal to 5 upon 2 into the budget constraint. Okay, so we get here 5x plus 3, rather we have 2 because the price of y is 2. So here we have also 2 times 5 upon 2 x is equal to 10. 2 and 2 gets cancelled. 5x plus 5x is 10x. So we get here 5x plus 5x is equal to 10, which implies, if I write it here, so this is 10x is equal to 10, dividing both sides by 10, x is equal to 1. X will be equal to 1. Okay, so at optimal, consumer will choose x star is 1. And what about good y? Plug x is equal to 1 in this equation. Okay, which implies y will be equal to 5 upon 2 times the value of x is 1, so we get here 1, so which is 5 upon 2, which is 2.5. So consumer will consume 2.5 units of good y to maximize his satisfaction. Okay, pretty simple. This question can also be solved by taking the Lagrange here. Okay, so let me show it here briefly. Okay, we can solve this question using Lagrange's method also. For that, what we need to do, so this will remain same, and our budget constraint, that is price of x times x plus price of y times y should be equal to income. Specifically, it will be equal to 5x plus 2y should be equal to 10. So in the Lagrangian method, what we do, we simplify this again. We solve it further here. We set it equal to 0 first, so we get 10 minus 5x minus 2y should be equal to 0. Then what will we do? We multiply both sides by lambda. Okay, when we solve it using Lagrange function, then we form the Lagrange function, which is equal to our utility function, which is x raised power 1 upon 2 times y raised power 1 upon 2, and to this we add the resulting constraint function, which we formed by first setting it equal to 0 and then multiplying both sides by lambda. So we add this resulting constant, that is 10 minus 5x minus 2y. Okay, this is our Lagrange function. Now to find out the optimal values of x, y and lambda, what we will do, we partially differentiate this Lagrange function with respect to x, y and lambda, solve them simultaneously. That is, we take L subscript x, means the partial derivative of this function with respect to x. So the derivative of x is 1 upon 2, x raised power minus 1 upon 2, y raised power 1 upon 2 will remain same. Then we have derivative of x is 1, so we are left with minus 5 times lambda, which is equal to minus 5 lambda, and we set it equal to 0. Similarly, L subscript y means the partial derivative of this Lagrange function with respect to y. Again, 1 upon 2, x raised power 1 upon 2 will remain same, y raised power 1 upon 2 will get subtracted because we are taking partials with respect to y. And the exponent, rather the derivative of y is 1, so we are left with minus 2 times lambda, which is minus 2 lambda is equal to 0. Then we take the partial with respect to lambda, So no lambda is involved in the first two terms. Lambda, derivative of lambda is 1, so we are left with 10 minus 5x minus 2y is equal to 0. If we further solve this here, so can I write it? If I transpose, minus 5 lambda becomes plus 5 lambda, it also becomes minus 2 lambda plus 2 lambda. Let us say this is equation first, this is equation second. What we do here, we divide equation first by equation second. Let us divide it here. Okay, so here you can see 1 upon 2 gets cancelled. We get y upon x is equal to 5 upon 2. Here lambda and lambda gets cancelled, or y is equal to 5 upon 2 times x. Then we plug the value of y is equal to 5 upon 2x either in this equation or in the given budget line. Okay, budget equation. So 5 times x plus 2 times the value of y again is 5 upon 2 times x should be equal to 10. 2 gets cancelled, rather 2 gets cancelled, so we get 5x plus 5x is equal to 10, which is equal to 10x will be equal to 10, or we get x is equal to 1. To find out the value of x, plug here the value of x, so y will be equal to 5 upon 2 times 1, which is 5 upon 2, which is 2.5. This is how do we solve it using Lagrange's method. Okay, I hope I make myself clear in this video and you find out this video helpful. Thank you.